Hello, boys and girls. My name is Tyrone Brown. Thank you for joining us for another thought provoking math lesson. Today, for our mathematics experience, we will be exploring how to find the area of a triangle given two sides and the angle they form. We will tackle finding the area of triangles which do not have right angles. Grab your calculators and a sheet of paper as we tackle these together. Before we start our expedition, I want to check in with you to see if you remember what area is, as this is the major focus of the lesson. So, what is area? Yes, area is defined as the measure or the size of the surface enclosed in a shape, or the surface of an object. Hence, we see the space enclosed in the boundary of our shape, which happens to be a triangle. This is the area of this shape. There are several ways we can find the area of a surface. This includes counting unit squares. How many square units does it take to cover this shape? Yes, you are correct. This shape is 8 unit squares. When we combine the 4 half squares, we get 2 holes, and another 6 holes gives us a total of 8 unit squares. As you can see, this is also a half of the area of 4 multiplied by 4. Therefore, we can say that this triangle is half the area of a square, or half of 4 multiplied by 4. In general, the height of a triangle can be found with the formula half of the base multiplied by the height. But can we use any height with this formula? You are correct. The height must be perpendicular to the base of the triangle. In this case, the perpendicular height is 10 meters and the base is 14 meters. What would be the area of this shape? You are correct. The area of this shape is 70 squared meters. This is found by taking half of 14, which is 7, and multiplying that number by 10. Suppose we needed to find the area of this shape. Could you think of 3 ways this could be done? Yes, we could start off by counting squares, which would give us an area of 14 unit squares. We could also use the formula half of the base multiplied by the height, which would give us half of 7, which is 3.5 multiplied by 4, giving us 14 unit squares. Additionally, we could break it into two right-angled triangles and find the total areas. This would be half of 3, which is 1.5 multiplied by 4, giving us 6 squared units for the first region, and half of 4, which is 2, multiplied by 4, giving us 8 unit squares for the second region. The total of 6 and 8 squared units would be 14 squared units. But what if we did not have the height perpendicular to the base of the triangle? Let's explore how we would handle such a situation. We know that the height of a triangle can be found using the formula half of the base multiplied by the perpendicular height. How can we find the perpendicular height h using our knowledge of trigonometry? You are correct. We can use the sine ratio, which is the length of the opposite side divided by the length of the hypotenuse. In this case, it would be h divided by a, and then transpose to get a value for h. This would be done by multiplying both sides by a, giving us a sine c as an expression for the height of the triangle. We can substitute this into our equation, and that becomes half of b multiplied by a sine c. But we as mathematicians like our variables in alphabetical order, so this becomes half ab sine c. Notice that the reference angle c is formed between the sides a and b. This angle is often referred to as the included angle. Okay, for this triangle, we can see that the two sides given have values of 5 and 7, and the included angle is 49 degrees. What would be the area of this shape? You are awesome. It is 13.2 squared units. That is found by multiplying half of 7 and multiplying that results by sine 49 degrees. Let's see what would happen if we used our formula to rework the area of this triangle. I will give you a few seconds to try it. Yes, we can see that we will get the same value for the area of the triangle, which is 70 squared units. This is half of 14 multiplied by 10 multiplied by sine 90 degrees. But I am sure you are wondering, why not use this formula for all triangles? You will notice that we use one additional step by finding the values of sine 90, which always has a value of 1. This will always have the same product since we are just multiplying by 1. It is often faster to just use half the base multiplied by the height when the perpendicular height is known. Let's explore an application of this concept. Your sister started a small business and wanted to create an innovative package for her design. She needs your help in finding the area of the triangular faces so she can determine the total materials required. Here is a sketch she gave to you. Do you notice that this face has two equal sides of 12 centimeters and the included angle is 50 degrees? Could you use half multiplied by the base multiplied by the perpendicular height to solve this question? You are correct. You do not have the value for the perpendicular height, and we know the values of two sides and the included angle. So we will use half AB sine C to solve this problem. I will give you 1 minute to try this question. Okay, we substituted our values into the formula half AB sine C and found that the area is 52.2 squared centimeters. This was found by multiplying a half times 12 times 12 multiplied by sine 50 degrees. But wait, we had 4 identical faces, so we will multiply this by 4, giving us a total of 220.8 squared centimeters to be our result. Let's try this CSEC question. The diagram below, not drawn to scale, shows the position of 3 tones, P, Q, and R. Calculate the area of PQR. I will give you 1 more minute to attempt this question. Okay, we substituted our values into the formula half AB sine C and found the area to be 3,517 squared kilometers. This was done by multiplying half of 120 multiplied by 150 multiplied by sine 23. You guys are just awesome. Let's recap. In today's lesson, we discovered that we could use the formula half AB sine C to find the area of a triangle when the perpendicular height was not known. We also discovered that we needed the lengths of two sides and the angle between them, which was also called the included angle, to utilize this formula. Finally, we realized that it was more efficient to use this formula when we do not have right angles or the perpendicular height. Awesome, boys and girls! Learning to calculate the area of a triangle in a different way was so much fun. See you again soon for another exciting lesson.